Monte Carlo simulation and the Black-Scholes model. How the heck are these connected? More importantly, how can we price options using Monte Carlo simulation and, of course, the Black-Scholes model? And are these prices the same? Well, I sure hope so. Let's dive right into trying to get a grip first on the relationship between an analytical expectation and a numerical expectation. We're going to use a simple example of a dice roll game, and then we'll build off of that into the option pricing argument. Okay, so I use some fancy terminology there. Let's start with this idea of an analytical expectation. All that means is there is a formula for the expected value of some random variable. This random variable could be a coin flip, a Bernoulli, it could be a series of coin flips, a binomial, it could be a continuous exponential random variable. Depending on the randomness that we are modeling, we are going to substitute in a different probability mass or density function into the equation, and we're going to use either a summation or an integral to accomplish this. So what I have here is the example in a discrete setting for something like a coin flip, series of coin flips, things of that nature. This is the formula for the expected value. If we scroll on down here, you'll see that we have an example of applying this formula to a coin flip that is a Bernoulli random variable, and we go through this argument here to prove that the equation for the expected value of a Bernoulli random variable is simply just the probability of success P, and we do that by applying this expected value formula. If we scroll down here to the continuous case, instead of a summation, we have an integral. Instead of a mass function, we have a density function, and we can apply this in the same capacity in a continuous setting and substituting in an exponential probability density function. And if we integrate across that entire region, we will get the closed form solution for the expected value. All this is to say is the analytical expectation is simply applying the formula for the expected value of a random variable in either the discrete or the continuous setting, discrete being something countable like 1, 2, 3, 4, things like coin flips, things like the number of blank out of blank binomial, Poisson random variables for arrivals, things of that nature. You can apply this formula or something continuous, think like a stock price or waiting time. Then you can apply this formula, and you're actually going to end up with an equation. So when I say analytical expectation, I'm actually talking about an equation, and this equation is derived using these definitions. And of course, once we have an equation, it's very, very easy to go about finding the expected value based on the parameters. So for example, if we have a coin flip and it's 50-50, the expected value is just going to be the probability of success, which in that case would be 0.5. If I had a weighted coin and the probability of success was 0.7, then my expectation would be 0.7. Moreover, down here, if I have some sort of exponential distribution parameterized by lambda 2, then the expected value for that exponential distribution would be 1/2, perhaps modeling wait time in minutes or something of that nature. If we scroll on down here, what I'm going to do is actually I'm going to visualize these distributions. So what I have here is I have a Bernoulli distribution, that's a coin flip, but this is going to be a weighted coin. The probability of success has a weight of 0.7. Probability of failure has a weight of 0.3. So you could think of this as heads and tails, success, failure. And then I also have an exponential distribution here parameterized by lambda equals 2. So this is the mass function over here, and this is the density function over here. And the analytical expectation, just as I had said before, for each of these respectively will be 0.7 and 0.5. And it's very, very easy to find the expected value of these random variables because we're able to just go about plugging in the parameters into the formula for the expected value that we've found by applying the formal definition for each of the discrete and continuous cases. Now, what if I can't use the definition of the expected value to find this equation? What I mean is, if we go back up to these definitions, we have a summation in the discrete sense, and we have an integral in the continuous sense. These may yield some very, very challenging equations to solve. And in some cases, they may be intractable. Intractable to mean we can't solve them analytically, as seen here, where we end up with just a nice explicit equation for the expected value. I just plug in P, and I find the expected value. I plug in lambda, I find the expected value. Sometimes we're going to get equations with this summation and with this integral that are absolutely crazy. Maybe it's over an infinite region that makes it very difficult to integrate or sum over. Maybe there's some weird product going on. Who knows? But the point is, these may be intractable to solve analytically. I may not be able to find a nice explicit closed form solution. So what can we do? What's our next best bet? Well, we can do something called Monte Carlo simulation. Monte Carlo simulation means I'm going to sample from these distributions. I'm going to draw randomly, boom, a Bernoulli, and then I'm either going to get a success or a failure. I'm going to draw from this exponential distribution, perhaps modeling wait time, and I'm going to get an example wait time. And if I continue to sample from these distributions, then what I can do is I can collect a set of these values. So I'm going to end up having success, success, failure, success, 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 failure. I'm going to have a set of values. I can add them all up, divide by the total number of draws, and I'm going to be able to compute a sample average. And I can do that in both the discrete and the continuous sense. So by being able to draw from these distributions, I can come up with an approximate average. And that's exactly what Monte Carlo simulation is. Instead of going out and sampling, say, maybe people, because I'm trying to compute maybe the average height of a population, I can just use Monte Carlo simulation to repeatedly draw from a distribution with a fixed parameter. So here the exponential has a fixed parameter of lambda equals 2. The Bernoulli has a fixed parameter of p equals 0.7. I can continue to draw from these, and then I can take the average, and I'll have an approximation for the true expectation. So what does that look like? Well, I have a little naive example here with 2 for loops. So what I'm going to do is I'm going to draw from the Bernoulli distribution, and I'm going to draw from the exponential distribution, and I'm going to take the average of the samples. And when I do that, what you'll see here is the Bernoulli Monte Carlo sample mean is 0.7011. Very, very close to the analytical 0.7, so it's very, very close. The exponential is 0.5023, again, very, very close to the analytical. Now, why does this work? Something that I feel is not drawn as a connection is why this sampling procedure works. I'm able to simulate draws from each of these distributions with a fixed parameter set, but why is it very close to the analytical value? We did not apply the formula. Remember, all we're doing is we're sampling these values, adding them all up, and then dividing by the total number of samples. And somehow we're close to the actual value given by the closed form solution in both of these examples. So why is this the case? Turns out this is no coincidence, and a lot of students hear about the law of large numbers and the central limit theorem and maybe even an AP statistics course back in high school, but rarely do we actually see what it means in the context of simulation, especially at that point in time. And what we have here is the law of large numbers stating that if we are to repeatedly sample from a distribution, and we sum up all of those values and divide by the total number of values, in this case, n is some arbitrary sample size. As n approaches infinity, that is, as our sample size becomes arbitrarily large, this value, 1 over n, the summation of all of our samples, is going to converge almost surely to our theoretical expectation. This is an incredible result. This is a very, very important and incredible result. I don't feel that the law of large numbers is appreciated as much as it should be, especially in the context of the central limit theorem, which pretty much takes center stage, especially in testing. But here, this result is the is the reason why we are able to do this Monte Carlo simulation and come up with an approximation for the expected value. That is the theoretical expected value. It's because it's going to converge almost surely to the theoretical expected value as the sample size becomes arbitrarily large. That is why we're able to do Monte Carlo simulation. That's why we're able to do Monte Carlo pricing. So in other words, if we can express an options price in terms of an expectation, that is this right-hand side, where x is the option price, then we can conduct Monte Carlo simulation to figure out an approximation for that price. And that is the connection between Monte Carlo simulation for pricing and closed form expressions like the Black-Scholes model for pricing. Let's see this in action. I've long said anytime you're dealing with randomness, you're really dealing with a game of uncertainty, and you can frame it as such. So what I like to do is I like to take a very simple example of some sort of game and apply these ideas, and then we can extend them to a more complicated game where we're trying to price some sort of financial derivative. In this case, we're going to look at option pricing in a Black-Scholes framework. So what we have here is this idea of analytical and numerical expectation, right? The numerical expectation converges almost surely to the theoretical analytical expectation, where the numerical expectation is just the Monte Carlo simulated average, the Monte Carlo simulation. What we have here is an example using a geometric distribution. So what I've done here is I've taken the probability mass function for a geometric distribution, and I've gone about solving for the theoretical expected value, 1 over p. In other words, if it takes me, let's say the probability of success is 1/2, then on average, that is the expectation, it will take me 1 over 0.5 to see the first success, so 2 trials. And that makes sense, right? If you have 2 trials and the probability of success is 50%, then you would expect to yield at least 1 success on average out of those 2 trials. So in the context of a game, what do we have here? Well, we have a geometric random variable where we are going to roll a dice until we get the number 6. So we can apply this solution that we just derived here, this closed form solution for the expected value, to this game where we just plug in 6, and we get 6 dice rolls is required on average to see the first 6. Okay, and that's the analytical solution. The Monte Carlo simulation is going to yield a very similar value, just as we saw above with the Bernoulli and exponential random variable example. Here what we're doing is we're drawing from that distribution. What I mean is we're going to roll a dice, roll a dice, roll a dice, roll a dice until we see a 6. We're going to keep doing that a whole bunch of times, and I'm going to record how many times it takes me to see a 6. Maybe it'll take me 1 try and I'll get super lucky. Maybe it'll take me 20. That's the whole point. We're going to keep doing this simulation again and again and again, and then we're going to take the average and see on average how many dice rolls are required to see that 6. We know the analytical solution is 6. This is given by our formula derived here. But if we simulate it a whole bunch of times, based on what we've shown here with the law of large numbers, we should see that this value is very close to the theoretical value for a large number of simulations. And over time, that will converge. And that's exactly what we have here. So if we start with a small number of simulations, you can see the average is about 6.4. But as n increases the number of simulations, we converge almost surely to the true expected value, and that is 6. So that's the connection between the analytical and numerical solution for the expectation. And this is in the framework of a game. So what we've done is we said, okay, like we're going to roll a dice until we get a 6. How can we model that? Well, we can model it as a geometric random variable. We know that there's a closed form solution for the expectation, but we also can simulate it, right? We can just roll a dice until we see a 6, record how many times it took us to see that first 6, and then take the average. And then the law of large numbers says that converges almost surely. And sure enough, this is what we get. We see that over time as the simulation number increases. So not over time, but as the total number of simulations increase, we converge to that theoretical expectation. Now we're ready to discuss option pricing. The Black-Scholes model assumes a stock that is an option written on some sort of underlying asset, and in this case the underlying asset is a stock, is going to follow a geometric Brownian motion. These are the dynamics of the stock price path. And the risk-neutral pricing, that is the fundamental theorem of asset pricing, says that in the absence of arbitrage, we have something called a risk-neutral measure Q, under which the discounted price process is a martingale. And that means for a European call option, we can present the price as the discounted, that is this e to the negative RT, risk-neutral expected payoff, where the payoff is given by S sub capital T. That is the stock price at the terminal point in time, capital T, less the strike, of course, taking the max between that and 0. So what is this actually saying? Well, this is saying that, hey, we have some stock price that's going to evolve throughout time governed by this equation here. At some point in the future, capital T, we're going to realize a payoff for this option. And that payoff is going to be the max between the terminal value less the strike price and 0. In other words, if there is a positive difference between the strike price and the terminal price, you'll exercise for profit. Otherwise, you're going to let it expire worthless because it makes no sense to exercise. So what is the present value of such a contract? Well, we don't know what the price is going to be in the future. The best we can do if we don't know the price in the future is to figure out the expected price today. So what we're going to do is we're going to compute this risk neutral expected payoff, and that is going to be the value of the call option today. What's the problem here? Well, this is one heck of an expectation to solve analytically for. Don't believe me? I have an article and a video walking through the entire derivation of the Black-Scholes model. Not just the Black-Scholes partial differential equation, that is that fundamental partial differential equation, but actually going about solving it. So I'm just going to show you a couple of the steps here. For the analytical solution, as we've seen above, this turns into a mess pretty darn quickly. So in the context of the geometric random variable for the fair dice roll game, this expanded pretty aggressively, pretty quickly. I even factored out a derivative here. And if you scroll on down to the Black-Scholes pricing argument, goodness gracious, we got a big argument here. We're going to construct a portfolio. We're going to do a hedge. We're going to apply Ito's lemma. We're going to go about deriving this fundamental partial differential equation. We're going to assume no arbitrage, implying that we earn a risk-free rate. And that's going to yield this Black-Scholes PDE. So I'm sorry, this wasn't even the Black-Scholes PDE. This was the first step after Ito's lemma. Then after constructing the no arbitrage argument, you get the PDE. Solving with the boundary condition yields the so-called Black-Scholes model formula. Again, I have plenty of resources available that actually go about step-by-step deriving this model. I'll link them in the description below. But nevertheless, this is the analytical solution. Now, what do we know about the analytical solution? This right here, this call price, is equal to this closed form solution. Just as above in the dice roll game, we have this closed form solution for the expectation. So what does that mean? Well, that means that we can just go and get the expected value, that is that fair price of the option, by plugging in the parameters for the option into this formula after we go about solving it analytically. But we know there's a connection between the analytical price and the simulated price, and that connection is available to us via the law of large numbers. That is, if I can simulate draws from a terminal distribution of the stock price, then I'm going to actually be able to compute the payoff. So what I mean is, in the Monte Carlo approach, what we're going to do is we're going to simulate the stock price following the dynamics of the geometric Brownian motion. And what we're going to do is we're going to simulate that price to time capital T. And when we do that, we can compute the payoff and discount it back to the present. And we're going to do that a whole bunch of times. And then what we can do is we can take the average of all of those discounted payoffs. When we do that, we're going to see that it converges almost surely to the true theoretical value, which is also given by this closed form solution, the so-called Black-Scholes model. Now again, that's a lot of words. Let's figure out what's going on here. Well, in the context of the Bernoulli and exponential that I gave earlier, I said, okay, in a Monte Carlo setting, let's fix the parameters 0.7 and 2.0, draw from the distribution, and we can show that if we take the average, it'll converge to the theoretical average, the theoretical expectation. Boom, that's exactly what happened. We did the exact same thing for the dice roll, and we showed here that over a larger number of simulations, it begins to converge to the theoretical average. Well, we're going to do the same thing, but it's a little more complicated in the context of options pricing, especially using a Black-Scholes framework. What we have here is not just the parameters for the option contract, but also the parameters for the stock price process. We have volatility, which is going to change the dynamics of the stock price path. We have the risk-free rate. We have the time to maturity of the option. We have the actual beginning underlying asset price, the spot price today, the price of the asset right now, if I was to go in the market and buy it, and of course the strike price. So we have all of these different levers to pull. What does that mean? That means I have to fix all of these parameters for my Monte Carlo simulation. That is, I'm going to lock in the strike price, time to maturity, risk-free rate, volatility. All of these things have to be locked in for my simulation. There are other models that let these parameters also evolve over time, perhaps capturing more relevant stylized facts like the leverage effect, volatility, clustering, so on and so forth. But those are more complicated models. We can discuss those in another video. The principle remains the same even for those models. Once the simulation begins, all of the fixed parameters in that set remain fixed. The things that evolve over time evolve over pre-described dynamics, just like the geometric Brownian motion. So what I've done here is I've conducted Monte Carlo pricing, and I've also printed the true Black-Scholes price given a fixed parameter set. And what you'll see here is this is the terminal stock price distribution. This is the option payoff distribution. And this over here is showing the convergence of the Monte Carlo simulated price to the true Black-Scholes price given a fixed parameter set. All I've done now is print the price at the end of the Monte Carlo simulation and print the price given by the Black-Scholes model. And look what you have here. You have the Monte Carlo price is 10.444 and the Black-Scholes price is 10.45. So it is certainly converging to that Black-Scholes price. Some closing thoughts as it pertains to option pricing using Monte Carlo simulation or closed form solutions like a Black-Scholes model. Analytical solutions are exact, they're fast, it's very convenient. Monte Carlo methods, yes, they are slower. You have to simulate price paths, especially when models are intractable and there is no analytical solution. Think of things like rough volatility. Monte Carlo methods are required to produce prices. However, that's very slow, especially in the live markets when you're trying to calibrate a model to, say, a market surface to generate prices. That is just not something that's going to be effective. We need fast, we need speed, we need to be able to calibrate instantly and produce prices instantly. If you're using some sort of esoteric model, then it may take too long to simulate, and by the time you converge to some sort of calibrated market prices, the prices are going to change again. Fortunately, there's some streams of literature using AI to try to learn the map between the parameter set. That is, remember how I said you have to fix the parameters prior to simulation? Well, there's a stream of literature that aims to learn these parameters relative to the terminal price that was simulated, and results seem encouraging in the sense that it's able to extrapolate prices relatively well, making the speed of convergence much faster for these, more esoteric models, maybe something like a rough model family, which is particularly powerful when the analytical solutions don't exist. But I've discussed this in a previous video. I'll link that in the description below as well. I just wanted to connect to some other areas of the current literature in conjunction with the analytical and numerical connection that we made earlier, thanks to the law of large numbers. I want to thank you so much for watching this video. I hope you enjoyed. I really like making the connection between analytical expectation and Monte Carlo simulated expectation, especially by taking a look at the law of large numbers and what it means practically to converge almost surely to a theoretical value. So that being said, thanks so much for watching. I'll see you in the next one.